Taylor series centered at x equals c. F of x equals f of c plus f prime of c x minus c plus the second derivative of c over 2 factorial times x minus c squared plus keep on going in that pattern. Here is the nth term, and then we could write this in summation notation from n equals 0 to infinity. If c equals 0, the series is called a Maclaurin series. Example, find a Taylor series for f of x equals e to the 5x centered at c equals 2. Find the first four non-zero terms, and then we will find the general term. F of 2, in this case, is equal to e to the 10th. Then we want to find the first derivative at 2, which is 5e to the 5x. And then when we evaluate, we get 5e to the 10th. The second derivative is equal to 25e to the 5x. So that'll be 25e to the 10th. Then here would be the fourth non-zero term. So the third derivative is 125e to the 5x, and that's equal to 125e to the 10th. The series is going to be e to the 10th plus 5e to the 10th times x minus 2, and then plus 25e to the 10th times x minus 2 squared, and that's going to be over 2 factorial, and then finally plus 125e to the 10th over 3 factorial times x minus 2 to the third. And then the general term is 5 to the n e to the 10th times x minus 2 to the nth over n factorial plus dot dot dot. Then when we write this in sigma notation, we'd go from n equals 0 to infinity of 5 to the nth e to the 10th times x minus 2 to the nth all over n factorial. Power series, f of x equals 1 over 1 minus x. And in order to get the series from this comes from a geometric series where a sub 1 is equal to 1 and r is equal to x. So the series is 1 plus x squared plus x to the third plus x to the fourth, keep on going in that manner. So if we write this in sigma notation, actually the nth term is just going to be x to the nth power. And then in sigma notation, we're going from 0 to infinity of x to the n. Now we know from the geometric series that the absolute value of x has to be less than 1 in order for this to converge. So negative 1 is less than x is less than 1. And so the interval of convergence is negative 1 to 1. That's your interval of convergence. Well, we've put this in the graphing calculator, and let's put it, I put in the first three terms, I put in the function also. So the skinny lines is the function 1 over 1 minus x, and then 1 plus x squared, that's going to be a parabola. And you can see right in the middle, centered at 0, this fits really well. Then I added a few more. I went x to the third, x to the fourth, x to the fifth. And again, even though we've added a few more terms, it's good in the middle, but then it falls apart as it widens out. Well, as it turns out, no matter how many terms you put in, you can go all the way up to x to the 7th, and the interval of convergence is from 1 to negative 1, or negative 1 to 1. In other words, the series works as long as you're very close to 0. This is a good representation of the power series, like I said, as long as you're from negative 1 to 1, else it gets really bad. There are three special Maclaurin series you must know. These are the series for e to the x, sine of x, and cosine of x. To derive a series for e to the x, we take the derivatives. And so we have f of x is equal to e to the x. And if we evaluate that at 0 for the Maclaurin, we get e to the 0, which is 1. And then f prime of x is also e to the x. And we're evaluating this at e to the 0, which is, again, 1. And then f double prime of x is equal to e to the x. Evaluate that at 0, and it's 1 again. And then f triple prime of x is equal to e to the x again, e to the 0, which is 1. So a good representation is 1 plus x plus x over x squared over 2 factorial plus x to the third over 3 factorial plus keep on going. So the nth term is x to the n over n factorial. So if we write that in summation notation, we get n equals 0 to infinity of x to the n over n factorial. Now if we plot a few terms of this one, you can see that it's very good for a few values centered at 0. But then if you put more in, here's your e to the x, the skinny line, then the approximation is getting better. And the approximation here is widening out. So the interval of convergence for e to the x is all reals. So interval of convergence for e to the x is not just -1 to 1, but for all reals, for all values. To derive a series for sine of x, we have f of x is equal to sine of x, and sine of 0 is 0. F prime of x is equal to cosine of x, and cosine of 0 is 1. The second derivative is equal to negative sine of x. That's 0. The third derivative is equal to negative cosine of x, and that's going to be -1 at 0. And then the fourth derivative, that's equal to sine of x, and we're right back where we started. We start at sine of x, and then sine of 0 is 0. So let's get the polynomial that estimates this function, sine of x. We start out with 0, and then we'd have x. Then the x squared would be 0, and the x to the third would be -1. So minus x to the third over 3 factorial. Then we'd have 0, and that would start right there. And then the next one, the x to the fifth, would be a +1. So then we have x to the fifth over 5 factorial. We'd have 0 again for x to the sixth, and then x to the seventh would be negative. So this is alternating signs, and it has the odd powers of x, and the odd powers are the odd values of the n factorial. So let's get the nth term now. First of all, let's say we're going to plug 0 in. If we plug 0 in, then we would have -1 to the nth power. We'd have x to the 2n plus 1. So if you plug 0 into 2n, you get 0 plus 1, that's 0. And then that's all over. We'd have, we need the odd. We need like 1 factorial and then 3 factorial. So we would need 2n plus 1 factorial. And this is if we plug 0 in, we would get this series. So then the sigma notation is n equals 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1 factorial. And that's the Maclaurin series for sine of x. But I want you to notice one thing. There's an kind of an easy way to remember this, in my opinion. If you graph sine, it looks like this. And sine is an odd function. If you pick a point on the right side of the origin, you go through the origin, let's try that again, through the origin, you get its reflection. Sine is an odd function, and look how we use the odd powers. Now let's see what the interval of convergence is, to see if does it converge on -1 to 1, or all reals, or what. So I've plugged in a few values, and it converges in the middle here, of course, centered around 0. More terms, it converges farther. More terms, it converges even better. But, eventually it fails. But what we see here is that sine converges on all values. Converges on all values. To derive a series for cosine, let's derive the series for cosine. To derive a series for cosine, we have f of x is equal to the cosine of x, and when we plug 0 in, we get 1. F prime of x is equal to negative sine of x. We plug 0 in, we get 0. The second derivative is equal to negative cosine of x, and that's going to be -1. The third derivative of x is equal to, this is going to be sine of x, that's sine of 0, 0. And then the fourth derivative, we are right back to where we started at cosine of x, and cosine of x is 1. So the polynomial that estimates this function is equal to, we start with 1, and then we have minus x squared over 2 factorial, plus x to the fourth over 4 factorial, minus x to the sixth over 6 factorial, plus keep on going in that manner. Now let's see what we get if we plug 0 in again. We're going to get negative 1 to the nth if we plug 0 in, and then x to the 2n over 2n factorial. Now if we write this with sigma notation, we have n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial. Cosine converges on all reals. Converges on all reals, on all values. Let's look at the graph of cosine. Cosine starts at 1, goes down, then back up. Then to the other side, it goes down and back up. But if you pick a point on the right side of the y-axis, you have its reflection on the left side. Now that means this is an even function. Look how we have even powers represented. Even factorials, even powers. And then you just have to remember that cosine alternates signs. We can manipulate these three special series, or any series we are given, to find other series by using the following techniques. Substitute into the series. Multiply or divide the series by a constant and or a variable. Add or subtract two series. And differentiate or integrate a series. Example, find the Maclaurin series for f of x equals sine of x squared. Well, let's get the Maclaurin series for sine of x. Sine of x is an odd function, so we need odd powers of x. We have x to the first minus x to the third over 3 factorial, plus x to the fifth over 5 factorial, minus x to the seventh over 7 factorial. And now, instead of doing, having sine of x, we need sine of x squared. So we can plug x squared into all of these. That makes x squared. And then we have x to the, well, think about what x squared plugged into x to the third. That's x to the sixth. And then x to the 10th. And then we have minus x to the, that's going to be to the 14th. Over 7 factorial, we got 5 factorial, we got 3 factorial. Plus keep on going in that manner. Let's get the nth term. So I don't really want an equals here. I want a plus. And then we need x to the, we have 2, 6, 10, 14. Now this keeps increasing by a power of 4. So we have x to the, if I plug in 0, I get 2. Plug in 1, I get 6. 4n plus 2. So I plug in 0, I get 2. Plug in 1, we get 6. Plus 2, that would be 8 plus 2 is 10. Plus 3, that'd be 14. That's going to be all over. We have, if we plug 0 in, that's going to be 2n plus 1 factorial. Those are odd. And then we need negative 1. I'm going to cram it in here. Negative 1 to the, it starts out with a positive, and we're going to start at 0, so that just needs to be an n right there. Now with sigma notation, we have n equals 0 to infinity of negative 1 to the n, x to the 4n plus 2, all over 2n plus 1 factorial. Find a Maclaurin series for f of x equals x cosine of x. Let's start out by just getting cosine of x. That is an even function, so we're going to start out with x to the 0, or just 1, and then minus x squared over 2 factorial, plus x to the fourth over 4 factorial, minus x to the sixth over 6 factorial, plus keep on going. Now we need, well, we're not going to get the nth term for this one, but let's multiply by x. We have x cosine of x. That's equal to x minus x to the third over 2 factorial, plus x to the fifth over 4 factorial, minus x to the seventh over 6 factorial plus, keep on going. Now look how the power has changed from even to odd, and they're also alternating. So we have negative 1 to the n if we start at 0, and then x to the, that's going to be 2n plus 1 over, we have 2n factorial. Now if we're going to write this in sigma notation, we have n equals 0 to infinity of negative 1 to the n, x to 2n plus 1 all over 2n factorial. Find a Maclaurin series for f of x equals e to the 2x. Well, let's get e to the x. That's equal to 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial, keep on going. Now we want e to the 2x, so we're replacing x with 2x. We have 1 plus 2x plus 4x squared plus 8x to the third over 3 factorial. I need a 2 factorial here. And then plus 16x to the fourth over 4 factorial plus, keep on going. Let's try to get the general term. And that is going to be, if we start at 0, that's going to be 2 to the n, x to the n over, we have n factorial. In summation notation, we have n equals 0 to infinity of 2x to the n over n factorial. Use your answer to A to find a Maclaurin series for the function h, given that h prime of x equals e to the 2x and h of 0 is equal to 3. What we're going to do is we're going to use this right here as h prime. All of that, actually all of this, we'll call this h prime of x right here, e to the 2x. Now we need to back up to h. In order to do that, we have to take the integral term by term. The integral of 1 is x. The integral of 2x is x squared. And then the integral of x squared is 1/2, actually 1/3, x to the third, but we still have this constant, and we have the 2 factorial constant. Then we have 8 over 4 times 3 factorial, x to the fourth, because you'll have x to the fourth, but then times 1/4. And then we'd have 16x to the fifth over 5 times 4 factorial, and we'd keep on going in that manner. Well, that's really equal to, actually, we'd also have plus c because we're integrating. But this h of 0 equals 3 takes care of that constant. We'll talk about that in a second here. Well, now we have c plus, really, we have x plus, we could have, we could do this. We could have 2x squared over 2 factorial. That 2 over 2 is still 1. And then we'd have 4x to the third over, this really turns into 3 factorial. It would be 1 times 2 times 3. That is 3 factorial. This is 1 times 2 times 3 times 4. That's 4 factorial. So plus 8x to the fourth over 4 factorial plus 16x to the fifth over 5 factorial, and keep on going. Well, what about this constant? Well, if we plug 0 into all of the variables, all of those become 0, and then that would be equal to 3. So the constant is just simply 3. Let's get that in there. 3 plus x plus 2x squared over 2 factorial plus 4x to the third over 3 factorial plus 8x to the fourth over 4 factorial, and so on. 16x to the fifth over 5 factorial. Let's get the nth term for this. And in order to get the nth term, the 3 really messes up any kind of pattern, so we're going to kind of cheat a little bit. We'll just put 3 out front. Now, if we're going to start at 0, well, let's just start at 1. It actually makes this a lot easier. We have x to the nth, because we have first, second, third. We'd have 2 to the n minus 1 over, and then we could have n factorial. Now, if we do this in summation notation, we have 3 plus the integral, not integral, but sigma notation, n equals 1 to infinity of 2 to the n minus 1, x to the nth over n factorial.